Yes, good morning, all the students. We have left with a topic in the last class. We'll complete that and go to the fourth lecture. In this chapter, we have seen what are neural networks and introduction to neural networks and how Perceptron acts as a basic unit in order to build the structure, complex structures of artificial neural networks, and what is the representational power of the perceptrons. Perceptrons can be used to represent many Boolean equations. Yet one single perceptron can't represent some of the Boolean equations, which can be still achieved by using multiple perceptrons, right? And in the next topic, we have seen what is the perceptron training rule. And today we are going to cover gradient descent and the delta rule. Now you understood what is the perceptron training rule, right? In this chapter, this is very important question, mark it. We have understood that perceptrons tries to adjust their weights in order to arrive at a most optimal hypothesis in order to represent the entire set of training examples. For that, this perceptron training rule will be useful. Each time in each iteration, the weights will be adjusted in order to reduce the error in the prediction. That is how we understood, right? In order to reduce the error in the prediction, whether the weight have to be increased or reduced, that will be taken care. If the error is too high, then the weights have to be increased or reduced in order to reduce that error in prediction. And if the prediction accuracy is very good, in that case, the weights will not be adjusted. That is called as the point of convergence, where no longer the weights will be adjusted. Okay, this is how the perceptron training rule works. Let us quickly run through this concept before going to the next concept. Even today afternoon, fifth hour also I am going to take. So let us go very slowly because all these are very important concepts in artificial neural networks, right? If you don't understand the basic concepts of this, you may not be able to build artificial neural networks and further deep neural networks. Deep learning, you might have heard about this term deep learning, right? Deep learning is nothing but having multiple layers of neural networks, complex structures of neural networks. But when you have to build those complex structures, you should be very much clear about the basic things that actually work in a neural network. That is why I'm trying to make the concepts very clear for you so that you can easily work or you can learn by yourself after say your course. You can try to learn by yourself to build these artificial neural networks in a complex way, right, in order to solve many problems. Because say simple neural networks may not be sufficient in order to analyze some images, or in order to identify some photographs, or in order to say identify some speech. In that cases, simple neural networks may not be sufficient. You should be able to build complex neural networks. Now, how to take a decision in order to build these complex neural networks? How many layers should be there? How many neurons should be there for each layer? How do you take that decision? Only when you know about these fundamental concepts, right? That is why focus on these concepts. It is very clear. I'll try to make it very clear for you. Okay, though mathematical concepts are involved, they are very simple concepts. Something like what you have studied in your 10th standard or PUC. Only those concepts, not very complex MSc mathematics concepts, are not there at all. Okay, so seeing this maths, you should not be worried at all. Just pay attention. I'll take you through. Okay. Now, let us see the perceptron training rule very quickly. The precise learning problem is to determine a weight vector that causes the perceptron to produce the correct plus or minus output for each of the given training examples. Okay, this example, this learning problem, let us take. Now, several algorithms are known to solve this problem. We know that, right? If it is beyond this value, fire this output, otherwise fire this output. We understood that with respect to the perceptron in a neural network. Now, here we are going to consider two rules, the perceptron rule and the delta rule. Let us see in which scenarios these will be used. both has some difference. I'll try to elaborate that further. Now, these two algorithms are guaranteed to converge to somewhat different acceptable hypotheses. Yeah, they are guaranteed to converge, but in a different way in order to reach the final ideal target function. You know what is an ideal target function, right? Ideal target function is the best fit to the training examples given. So that if a new data point is given and the parameters are substituted into that say hypothesis, immediately it should be able to predict with as much accuracy as possible. Okay, that is called as acceptable hypothesis or target function, ideal target function, acceptable target function, right? In the first chapter, we have got that ideal target function as y equal to w1x1, w2x2, w3x3, and so on up to w6x6 when we considered 6 board states in order to make the next move. Now, how best is the move? That will be decided by the weights associated with those board states. Okay, so which board state has to be taken with seriousness? Which board state is okay, not to consider much? Like that, different weights will be given. Now, this will arrive at a point of convergence where the weights will no longer be changed, and that is the ideal target solution. Now, whenever a next move have to be made, immediately this board states, that current board states can be taken and with their associated weights. These associated weights will be determined by the least mean squares algorithm. You remember in the first chapter, you have least mean squares algorithm. When you substitute in that, immediately you will be able to assess the next best move, next optimal move. Okay, in the same way here, these two rules, perceptron rule and delta rule, or these two algorithms, they will help us to make some acceptable hypothesis, arrive at some acceptable hypothesis. They are important to artificial neural networks because they provide basis for learning networks of many units also, not only with single unit, multiple perceptrons. You might have heard about this MLP, multi-layer perceptron, where there are many layers of the perceptron, which forms a complex structure of artificial neural networks that performs evaluation very easily, very quickly, though the training time is little longer. Okay, that you have seen in appropriate problems for artificial neural networks, right? Though the training time is much longer compared to other algorithms, compared to other models, evaluation time is very less. It will take decisions very quickly. That is why artificial neural networks are being appreciated in many fields. They are being applied in many fields. Now, one way to learn an acceptable weight vector is to begin with random weights. You can start off with some random weights, then iteratively apply the perceptron for each training example, modifying the perceptron weights whenever it misclassifies an example. Okay, this process is repeated, iterating through the training examples one after the other as many times as needed until the perceptron classifies all the training examples correctly. When the perceptron classifies all the training examples correctly, the prediction accuracy is high. When the prediction accuracy has reached its point of convergence, you need not adjust the weights any longer. That is what we mean here. Now, what is the perceptron training rule? Wi equal to Wi plus delta Wi. Delta denotes some change. In any field, when we use delta, it denotes some change. Now, when we are using this delta Wi and adding it to the old weight, you will get the new weight to which it has to be adjusted. Why this adjustment have to take place? Because there is some prediction error. Now, how this delta Wi is calculated? It is nothing but the learning rate multiplied by what is the target value in the training examples and what is predicted by the algorithm multiplied by the input value. Okay, this will give you the delta value that have to be adjusted or that have to be added or subtracted from the old weight in order to get the new weight adjustment. That reduces this prediction error, T minus O. Right? And I also explain you very clearly what is the learning rate. Initially, the learning rate will be larger, but as it comes towards the point of convergence, reaching the ideal target function, the learning rate has to be reduced so that it doesn't overshoot its target. Means it doesn't cross its target. That I have explained you with the mountain climbing example or mountain descent. We can apply in both cases. When descending a mountain or when climbing a mountain, initially you can take larger steps, but as you come to the destination, you can take smaller. You have to take smaller steps so that you will not miss your destination. Right? So I'll give you a better example. Say you're trying to find out a friend whom you have, find out the friend's house whom you have met on Facebook, your old friend. Okay, so he has given you that he stays in Delhi in some street. Right? Now, initially to reach Delhi, you'll take longer steps, means you'll go in a train or flight, very quick steps. But after going there, as you approach the street, you start taking smaller steps and inspect each and every house address in order to find out the correct address, right? That is how the learning rate works. Initially, the new, this is called as new, N. We write it like this. Okay, this new, initially it will be larger, but as it reaches its destination, means as it reaches correct prediction, it will try to learn smaller steps to reach the destination appropriately. Once it reaches the destination, means once it starts making predictions correctly, then no longer it has to learn anything. No weight adjustments have to be done. In that case, it will converge there, means no weight adjustments will further be done. That is why here we indicated that the learning rate will decay as the point of convergence is met by the weights. Okay, learning rate, this will decay, means no more learning needs to be done. It will be completely, it vanishes. Okay, learning rate doesn't exist any longer once the weights have reached their point of convergence, means no longer the weights need to be adjusted. Okay, now how this calculation is done is given here. How this delta Wi is calculated is given here. Xi, if it is 0.8 and the learning rate is 0.1, and T, the training example outcome is 1, but actually the prediction made is -1. In that case, how to calculate the change that has to be made to the weight? This formula, nu T minus O, the prediction error. This T minus O is called as the prediction error multiplied by the input value. So it is 0.1, the learning rate, 1, the training example target value, -1, the predicted target value multiplied by 0.8. So you will get here 0.16. So that is the weight that has to be added to the previous weight in order to make that prediction correct. Say if the target example, the training example's target value is -1 and it is predicted as 1, then when we calculate, we'll get it as -0.16. Means that much weight have to be reduced from the previous weight in order to make this particular prediction correct. This is called as the Perceptron training rule. By using this training rule, the Perceptron tries to adjust its weights in order to make the predictions as accurate as possible. Right? But if the data are not linearly separable, what will happen? In that case, convergence is not assured. I have given this hyperplane example. Say you have values like this. In this case, we can say they are linearly separable, so that all plus positive training examples fall on one side of the line and negative examples fall on other side of the line. But if you have something like this, then it is hard to separate them linearly, because if I do like this, you'll get plus value on this side. If I do like this, you'll get plus value on this side. So it is not a clear classification. In that case, you may have to draw a non-linear line. That in that case we call them as non-linearly separable. Right? Now, if the data is not linearly separable, then the convergence of weights is not assured, because it will keep on adjusting the weights infinitely, as the linearly separable line is not a best suit for fitting the data. Right? In that case, we may have to go for some non-linear equations. Our decision is wrong that linear equation will fit this kind of non-separable classes. In that case, we have to go for non-linear equations, which better explains the behavior of the data, which better classifies the data. Right? That is how we are proceeding to the next concept, that is delta rule. Initially, we learned perceptron training rule, which will best suit for linearly separable problems. But when the data is combined, somewhat there is no clear classifiable group of classes. Classifiable group of data points. In that case, you can't fit a linearly separable line. You may have to go for non-linear line. So sometimes you may even have to draw a line like this in order to separate the data. But what is the equation that best explains this non-linear line? How the weight adjustments will be done? That will we can understand from this concept, gradient descent and the delta rule. Okay, now this is new concept, right? I haven't done in the last class. Pay attention, students. Although the perceptron rule finds a successful weight vector when the training examples are linearly separable, it can fail to converge if the examples are not linearly separable, right? This is how I have set the context for you. I have set the platform for you in order to go further to learn this delta rule. Okay, so you understood this point. When the data is not linearly separable, then perceptron training rule may not explain the behavior of the data properly. In that case, a second training rule called the delta rule is designed to overcome this difficulty. Right? If the training examples are not linearly separable, the delta rule converges towards a best fit approximation to the target concept. Okay, let us see what is this delta rule. The key idea behind the delta rule is to use gradient descent to search the hypothesis space of possible weight vectors. You know what is a weight vector, right? When I say a weight vector, I represent it with this arrow, and that is the combination of W1, W2, W3, and so on up to Wn, right? The combination of all these weight elements is called as the weight vector. And when I say weight vector, I have to represent it with this arrow. It is nothing but it has magnitude and direction. In physics, we represent like this, right? So the key idea behind the delta rule is to use gradient descent to search the hypothesis space of possible weight vectors, to find the weights that best fit the training examples. Same thing we have seen in perceptron training rule also. Now let us see what is actually different from the perceptron training rule. This rule is important because why? Gradient descent provides the basis for the backpropagation algorithm. That backpropagation algorithm you're going to cover in this chapter itself as your next topic. Okay, which can learn networks with many interconnected units when you have complex structure of neural networks. In that case, this gradient descent will be useful. Now I have already given an example for gradient descent. When you're descending a mountain, say there is I'll explain it once again because many of the students might have not concentrated in your previous class. Or any of you students can explain what is a gradient descent when descending a mountain and you're at the top of the mountain. Now you have to reach the foot of the mountain. In that case, how do you proceed further? Can anybody explain? Okay. So this gradient descent problem is understood with respect and by taking the example of a man descending a mountain. He doesn't have any compass in order to descend the mountain, in which direction he has to go. In that case, think he is blindfolded. In that case, he just checks around him and he locates the steepest inclination. Say, if he goes in this direction, the mountain is still flat. But if he goes in this direction, it has some inclination downwards. So he can move in that direction. He'll take a decision. Means he has learned something that he has to go in this direction. That is called as the learning rate, which is represented by nu. Now, after reaching this point, again he'll search around him where there is best inclination to go downwards. There he selects that point and goes further down. What is he doing? He's trying to find the local optimal solution. He's trying to find out the local optimal inclination where he can proceed further downwards. But initially the steps he is taking are little longer. But as he comes towards the foot of the mountain, if he takes a larger step, he may cross his destination. That is why he has to take smaller steps. Okay, each time finding his local optimum. When I'm saying local optimum, his local best solution. He doesn't know the global best solution. Global best solution is this. But in order to reach that global best solution, he has to check his local solutions to move forward because he doesn't have any compass in his hand, remember. Okay, so finally he reaches his destination by making his learning rate smaller and smaller so that he doesn't overshoot his destination. He doesn't cross his destination. This is called as gradient descent problem. Remember, there will be only one global minimum for this mountain, but there are many local minimums. Say in this case, the mountain may be little curved. In that case, what is the local minimum? He has to check and proceed further. But to the mountain, he want to reach a destination means that is his global minimum. Okay, globally, overall, when you take the mountain, he has one minimum point to reach. But when he is proceeding further at each step, he has local minimum at each step. In that direction only he has to proceed. This is called as gradient descent rule. Okay, this is how a person learns to descend, or this is how an algorithm learns to reduce the prediction error. What is the goal of this person to reach the foot of the mountain? What is the goal of delta rule or perceptron rule? To reduce the prediction error. In order to reduce the prediction error, they're arriving at some target function, right? This is the target function for the perceptron rule or the delta rule. Now, to arrive at that target function, they are checking each and every possible weight which reduces the prediction error and finally arrives at best accuracy. Got it? Now, this rule is important because, yeah, it is used in backpropagation algorithm. Now, the delta training rule is best understood by considering the task of training an unthresholded perceptron. There is no specific threshold that we maintain. Normally in perceptron, what we do, beyond a threshold, this output have to be fired. Say greater than 0, it has to fire +1. If the linear equation solution is lesser than 0, it has to fire -1. But the delta training rule is best understood by considering the task of training as unthresholded perceptron. Unthresholded perceptron means you don't have any specific cutoff value. In that case, how the algorithm, the model is trained by using this delta training rule that we have to see. That is a linear unit for which output O is given by, how is it given? Output O is nothing but the multiplied, the dot producted value of weight vectors and the input vectors. So what are the weight vectors you have? W1, W2 and so on. What are the input vector input elements you have? X1, X2 and so on. Now, what is the dot product between them? W1x1 plus W2x2 and so on, right? This is your output vector, which is a combination of elements. Each element is the product of the weight and its associated input, or better say input and its associated weight, right? This is how we represent the output. In order to derive a weight learning rule for linear units, let us begin by specifying a measure for the training error of a hypothesis, that is the weight vector, relative to the training examples. I'll explain you better here. Now, although there are many ways to define this error, one common measure that will turn out to be especially convenient is using the sum squared error. You remember SSE, what you studied in your first chapter? There are many ways to define how the prediction error can be calculated, but the most common measure that you take is SSE, sum squared error. What is the error? What is the target label of the training example and what is the prediction made? The difference between them, square them, and for every training example, sum up all the errors. Okay, say for training example 1, there is some prediction error. For training example 2, there is some prediction error. Now, all these errors have to be squared and summed up, and that is halved. That is defined as the error. Okay, so what you're doing here, you're summing up all the prediction errors where D belongs to D, means this D is every training example. D is set of all training examples and small d is every training example. Okay, each training example you're considering. Now each training example's prediction error, it is squared, and sigma means it is summed up. All the training examples are summed up and the entire value is divided by 2, means it is halved. Okay, here we have given, see, D is the set of training examples, TD is the target output for training example D, and OD is the output of the linear unit for training examples D. In that case, you calculate the error, or you calculate the error measure. We call it as error measure with this formula. This is somewhat same like least mean squares approach, correct? You remember in the first chapter, sum squared errors. This is same as that. Okay. Any doubt in this, students?
No, ma'am.
This is how the error is calculated. So the target of this delta rule or gradient descent rule is to reduce this error by adjusting the weights. That is why it is error measure on the weight vector. Did you notice that? It is error measure on the weight vector, and it tends to adjust these weights in order to reduce this error, the sum squared error, prediction error over the training examples. Right? This is called as delta rule or gradient descent rule. Remember, these two concepts are very important in this chapter because these form the basis to understand how the model tries to reduce its prediction error. Now, what is the time? Yeah, we have sufficient time. We can start the fourth lecture also and cover up to some extent, so that in the afternoon class we'll complete that lecture 4. Now we are going to learn visualizing the hypothesis space and derivation of the gradient descent rule. Let us just answer these questions. I didn't, one second. Yeah, answer these questions. What is new? These questions I have asked in the last class also, but nobody responded except 1 or 2 students. What is new? Student, in perceptron training rule, we have like this, right? New into T minus O multiplied by the input value xi. What is new in this? Speak out, students. See how much effort we are putting to make you learn the concept. Are you understanding that? For 1 hour lecture, we are preparing for 2 hours to make it as much clear for you as possible. And after that 1 hour continuously we are speaking. For speaking, for answering for a moment, 1 or 2 seconds, you are feeling it that difficult, students? What is new? Not even one can answer this. Already some students answered this in the last class. Until you answer, I am not going to proceed further. Is it that difficult question, students? What is new? Are you there? Should I pick someone to ask? Surya? Surya, you are there?
Yes,
Sridhar?
ma'am.
Yeah, what is new? Sridhar?
Yes, ma'am.
What is new? For how much time I explained what is new, because that is very important in this perceptron training rule, right? Only on the adjustment of this new, the model will be able to reduce the training error. Prediction error. Umehani,
Yes, ma'am.
what
It
is
is
new?
positive constant learning rate, ma'am.
Learning rate. Why you didn't answer before me calling you personally?
I was about to, ma'am. You called Surya, so
Okay. After calling so many times, that is your moral responsibility. When teacher asks the class to answer something, you have to come forward voluntarily to answer. I need not ask you those many times. Learning rate. New is the learning rate. It's a constant. And that is constant for each iteration, not continuously, right? So for every iteration, the learning rate will start reducing. Initially, the learning rate will be high, but as it proceeds, the learning rate will reduce so that it will not cross the destination. Okay, it will not cross the optimal solution, it will not miss the optimal solution. Okay, say this is your optimal solution. If it takes a bigger step, it may cross this optimal solution. Optimal solution means where the prediction error is reduced. That is called your optimal solution. So in order to not overshoot its destination, though initially it has taken bigger steps, it has to take smaller steps to reach the final solution, right? This is the final solution. So the learning rate, initially you can keep it as 0, 1, but later you may have to change it to 0.01. Not you, algorithm will change it. 0.001, and finally when the weight adjustments need not be done any longer, in that case it means that this new will become 0. You need not adjust anymore the weights. Means no learning rate is required. Already it has reached its target solution. So the learning rate will become 0. Okay, that much story is there behind this new, and you're not answering that. At least learning rate, if you answer also, that will be sufficient, no? Okay, what is the perceptron training rule? Just the equation, can anybody give?
Algorithm algorithm would automatically weight optimal coefficients, ma'am.
Very good. It will automatically adjust the weight quotients so that it reaches optimal quotients. Very good. So it is Wi plus the change that has to be made to Wi. Change is denoted by delta. Okay, so it is delta Wi. This is the old weight. This is the change that has to be made in order to get the new weight, right? To the old weight, you're making some change, or sorry, algorithm is making some change in order to get the new weight adjusted to reduce the prediction error. Okay, this is called as the perceptron training rule. And how is delta Wi calculated? It is nu into the prediction error multiplied by the input element. That, yeah, xi. That is for each of the values, right? For each of the values, this is calculated for every input value. For x1, W1 is calculated. For x2, W2 is calculated. For x3, W3 is calculated, like that. Okay. Now, what is the delta rule?
It will update the weights.
It will update the weights. Here also it will update the weights. Where it is more suitable, perceptron training rule, for which kind of problems? Linearly separable problems or non-linearly separable problems? You understood what is linearly separable problem, right? If you have plus, plus, plus and minus, 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 you can draw a separate line. You can easily classify them. But if you have plus, minus, plus and minus, minus, can you easily separate them? No, right? Those are called as non-linearly separable. Now, in which case perceptron training rule is suitable? Which type of problems? Linearly separable or non-linearly separable?
Linearly.
Very good. Yes, yes. Linearly separable problems, perceptron training rule is suitable. Whereas in non-linearly separable problem case, you have to take the delta rule. That will make an approximation of the target function. So what is the rule here? Sigma, you take every training example that belongs to the training example set D. What do you do here? You take the square of the prediction error, the target value for the training example D and the predicted value, the difference between them, the prediction error, square it, and all training examples prediction error, square them, add them, and divide by 2. Okay, that will give you the delta rule. That is the error measure on the weight vector W, which will adjust the weight vector W bar. Got it? This is how we need to understand delta rule. Any doubts still here, students? I'll just give you an introduction to the next concept. And I'll end the class within 5 minutes so that you'll have a break for 5 minutes. Okay, in this, one second. Now in this lecture, we are going to see how the hypothesis space is visualized and derivation of the gradient descent rule. This derivation is little mathematical, but it is quite easy. You will be able to remember your PUC days, how you have done partial derivations and all. Why we actually do this differentiation or derivations, partial derivations, complete derivations, you might have remembered, right? That we are going to see in this class. Before that, this is a small concept. Let me cover this, and in the afternoon class, we'll go to the derivation of gradient rule. Visualizing the hypothesis space. In order to understand the gradient descent algorithm, it is helpful to visualize the entire hypothesis space of possible weight vectors and their associated e-values. E-values means error values. Okay, if with a weight vector 1, you're having a prediction error, you're adding delta W1 in order to make the new vector W1. Right? This you understood, correct? To the old weight, you're adding a small change in order to get the new weight, which will reduce this prediction error, overall prediction error. Okay, so to understand the gradient descent algorithm, it is helpful to visualize the entire hypothesis space of possible weight vectors and their associated E values. How do you represent it? You're taking it as a two-dimensional space in this case, or not a three-dimensional space in this case. See, the x and y axis here represents W0 and W1, whereas this z axis, that is a projection upwards, it represents the error. Okay, now when you try to fold this entire space like a cup, like this, in that case, what you're trying to represent here is, initially you may be somewhere here or here or here in predictions. Okay, but what is your actual prediction that has to be made? Somewhere here. Now, what is the difference between these two? That is the prediction error, EW. Okay, now how to adjust those weights in order to reach the minimum prediction error? This is your minimum prediction error, or that is called as the global minimum. Remember, global minimum means there will be only one best solution which will make your prediction errors as less as possible. So that global minimum will fall somewhere here and your predictions are somewhere here. Now you have to reduce this error. You have to reduce this difference between the predicted value and the actual value, this value. Okay, so you start from here, come here, adjust the weights, come here, adjust the weights, come here, adjust the weights. See, that travel, that journey is a random journey. You doesn't know what is the global minimum. You're making a guess of it. You're making an approximation where the prediction error will be very less. That is just an estimation. It's an approximation. You're just going blindfolded. The model is just going blindfolded. It doesn't know what is the appropriate solution which makes the prediction error very less. That is why it is checking at each stage. What is the prediction error? It is high. Adjust the weights. What is the prediction error? It is low. Make very less adjustment to the weights. What is the prediction error? It is proper. Means, what is the prediction error? It is as minimum, as much less as compared to previous prediction errors. In that case, yes, it has reached its optimal solution. You no longer need to adjust the weights. That is how you need to understand this hypothesis space. Wherever you take it is, wherever you take the hypothesis space and calculating the prediction error, you can represent it like a parabola. Okay, initially this is like a parabola, right? This is like a parabola. So you start somewhere here and try to reach the global minimum. This point is called as the global minimum. At each stage, it is checking its local minimum. Okay, local minimum means every iteration, what is the prediction error? Every iteration, what is the prediction error? Based on the prediction error, it is adjusting the weights and proceeding further. Okay, so it is trying to find out the local minimum, proceeding further in order to reach the global minimum. I'm repeating this. This is very important sentence. You have to remember this. When you go for interviews for machine learning experts, they'll ask this kind of questions. What is gradient descent? What is learning rate? You should be able to answer, because these are all hyperparameters which will make your model more and more efficient. So you should know everything in and out of these parameters, how they have to be adjusted in order to get the best accuracy from your model. That is why understand this carefully. Initially, you start from a point and proceed towards reducing the prediction error. How do you proceed towards the prediction error? How do you proceed towards reducing the prediction error? By finding your local minimum. Okay, at this stage, if I make this adjustment, the prediction error will be reduced. But that is the best reduction in the prediction error? No, it is just the local minimum. Among its possible solutions, this is the best weight adjustment to reduce the prediction error. Then proceed further. This is best local solution. Proceed further. Proceed further. Local best solution. Proceed further until it reaches the best of all the minimum prediction error. That will be your global prediction error. That will be your global reduction in the prediction error, That will be your global minimum of the prediction error. That is your optimal solution, right? That is how you need to adjust the weights in order to reach this global minimum. This is how we can visualize the hypothesis space. In next class, we'll discuss more elaborately on this topic, and further we'll derive the gradient descent rule. Students, try to make the classes interactive, because this is little complex topic what we are discussing. If you answer back to me, I can understand whether you understood the topic. Should I repeat it again or should I go slow? I can understand. That's why try to answer. If it is wrong also, not a problem. But if you answer based on your understanding, I can change my way of explanation. That is why. Okay, we'll meet in the next class. Bye.